This video lecture is going to be on covering periodic trends. This slide I'm just starting with to make sure I'm being super clear about what you're expected to know about the periodic table. So in case you missed it in one of our previous classes or you didn't write everything down, this is the information and stuff I would expect you to know where that is on the periodic table. So your periods, your rows versus your groups, your families, where the S, P, D, and F sublevel regions are, where metals, metalloids, and nonmetals are on the periodic table, as well as your common main group elements, your alkali metals, your alkaline earth metals, transition metals, halogens, noble gases, lanthanide and actinide series, and also like columns 13, 14, 15, and 16 with like the boron family, the carbon family, the nitrogen family, the oxygen family. But notice in red here that I have common properties. So you need to know what makes the alkali metals different than the halogens or the noble gases. So just make sure that you know that information, but this video lectures we're going to cover periodic trends. So periodic trends, there are other patterns, other information we can gather based on how the periodic table is arranged, and they are patterns that go in specific directions, so either across the periodic table or down, like from left to right typically we talk about, or either going down a family, down a group, from top to bottom on the periodic table. And so I'm going to explain all of these trends in terms of these important concepts: Coulombic attraction, nuclear charge, or effective nuclear charge, and electron shielding. So these topics were covered more in depth in the POGIL activity that we did in class on Coulombic attraction. So I'm going to summarize that, but these concepts can be reviewed in that packet. So once you understand these concepts, you can apply them to the trends we're going to talk about. So these were the two questions I posed in class based on the POGIL activity. So one was, how does electron distance from the nucleus, meaning how does electrons distance from protons, affect attractive forces within an atom, that Coulombic attraction? And how does the number of protons in the nucleus, that effective nuclear charge, affect forces of attraction? So now I'm going to answer those questions, but those were what that packet was covering through the examples in the POGIL activity that we did. What explains periodic trends is the arrangement of electrons around the nucleus and how many protons there are in the nucleus. So this idea of Coulombic attraction, this idea that opposite charges attract, so electrons are attracted to protons and protons attracted to electrons. Okay, so since we already learned where electrons are, okay, in their energy levels, their sublevels, and certain regions around the nucleus, now we can apply that to other trends. So let's start with Coulombic attraction. It is most affected by distance of electrons from the nucleus. So how far away electrons are from the protons is the single biggest contributor to any trend or pattern we're going to cover. So here's why. As you go down the periodic table, okay, you're adding more energy levels. Okay, so electrons are being placed in distances further and further away from the nucleus of an atom. So electrons are further away. And if they're further away, they have they feel less attractive forces from the protons just because they're simply further away. It's like as you get two magnets closer and closer together, they become more and more attracted. Okay, they repel one another if they are flipped the right way. So the more energy levels there are, meaning the further the distance away, the less attraction or pull those outermost electrons feel by the protons in the nucleus. And so in addition to that, lower energy electrons, so say you have an atom with, electrons on the first, second, and third energy level, okay? The electrons on the lower energy levels, the first and the second, they create a shield. It's kind of like they're preventing the electrons further away from feeling the full attractive force, the full attraction of the protons in the nucleus, simply because they're closer, and then they're kind of blocking or getting in the way of those electrons that are on higher energy levels. So not only does the distance affect it, but electron shielding from electrons in lower energy levels creates a less attractive force. So the further electrons are away, the less attracted they are to the nucleus. Now, we're going to talk about which, if you go across the periodic table or if you go from top to bottom down the periodic table, what is affected more. So, as I kind of already stated, distance is most affected as you go down a family or a group in the periodic table. And that's because you're adding energy levels. We're going to see that as you go, and hopefully as you know, that as you go across the periodic table from left to right, the distance is constant. You're adding electrons to essentially the same physical space as you go across. Like if you go across row 2, period 2, you're adding electrons to the second energy level in the S and P sublevels. Both of those are about the same distance. And so as you go across the periodic table, you're adding electrons to the same energy level, so distance is constant. But as you go down, you're adding new energy levels. And so distance is going to increase as you go down a group. So if we look here at this images, all right, this is trying to show beryllium with 4 protons in the nucleus, and this one's trying to show calcium with 20 protons in the nucleus. And so what I just want you to see here is that in beryllium there's 2 energy levels of electrons, okay? So these outermost electrons are only shielded or a little bit further away than electrons in the first energy level, okay? Now if you go to calcium, it's got the first energy level, the 2 in the first energy level. It's got the 8 in the second energy level, 2 from the S and 6 from the P. Then it's got 8 more in the third energy level, and then 2 finally on the fourth energy level for that 4s2. So what happens is not only you can see that the size of the atom is larger, okay, but these outermost electrons here, they don't feel as strong of a pull to the nucleus because of their distance, and also because all these other electrons on the first, second, and third energy level are getting in the way. Okay, so that's hopefully that image kind of showcases this idea of Coulombic attraction and how distance plays a factor in this. Now let's look at effective nuclear charge, because if you look at this image, beryllium has an effective nuclear charge of 4 protons versus 20 in calcium. So how does more protons affect Coulombic attraction? More protons, you would think, more attractive forces. So the definition of a nuclear charge is the attractive force or pull electrons feel from the nucleus. And as you would think, more protons, more attractive pull. Okay? How does this play in with distance, though? So this is the major force as you go across the periodic table. So distance was the major force as you go down. This is the major force as you go across. Okay, and that's because you're adding electrons to the same energy level as you go across. So think from left to right on the periodic table, across, staying in the same energy level. Okay, and what's going to happen is, if you think about that second row, from lithium to neon, all right, if you're looking at your periodic table, from lithium to neon, you are adding electrons all to that second energy level. However, lithium has 3 protons in the nucleus versus neon has 10. So as you go across the periodic table, okay, the effective nuclear charge is going to increase as you go from left to right on the periodic table across a row. And that's because you're adding electrons to the same energy level, but now you're adding more protons. So those electrons are going to feel a greater pull. So nuclear charge increases as you go across, and distance increases as you go down. Now we're going to see how these concepts apply to actual trends.